Interactive video world models promise a fundamental shift in how we simulate environments, generating future visual states from observations and actions without an explicit graphics engine. But for interactive deployment, you face a brutal constraint. You need causal generation, persistent responsiveness to game-native controls, and enough denoising speed to close the control loop. Recent systems have demonstrated auto-regressive generation with keyboard and mouse control, yet aggressive sampling compression creates a vicious cycle. Visual, action, and cache errors feed into subsequent chunks, coupling fidelity, controllability, and multi-chunk stability. When you reduce denoising steps, errors in the causal state amplify and propagate autoregressively. This is especially catastrophic for game-native controls, where discrete keyboard states and continuous mouse motion must remain perfectly aligned with temporally compressed latent chunks. Today, we're breaking down ForgeWM, a new framework that solves this through progressive causal training. ForgeWM transforms a bidirectional action condition generator into efficient, budget-specialized few-step world models using a four-stage recipe: domain adaptation, teacher-forced causal training, causal consistency distillation, and on-policy distribution matching. We'll dive into the technical architecture, the specific loss functions, the action conditioning module, and the novel Replay-Time Refinement protocol. Let's start with the problem setup and the base generator. ForgeWM builds on the matrix game lineage, using a flow matching objective. The generator receives the encoded first frame via channel-wise latent conditioning and a visual context branch. The flow matching objective constructs a path coordinate using noise level sigma and Gaussian noise epsilon. The velocity predictor is trained to match the ground truth velocity epsilon minus z. The induced clean prediction, which is the quantity compared in consistency and distribution matching stages, is derived directly from this velocity. The critical innovation for interactivity lies in the action conditioning. Unlike methods that reduce controls to camera poses, ForgeWM preserves frame-aligned, discrete, and continuous game-native controls. The action module injects these through separate pathways. Discrete inputs serve as cross-attention keys and values. Windowed continuous inputs are fused with visual features and processed by temporal attention. The VAE compresses 4 video frames into one latent frame. Each 3 latent causal chunk spans 12 video frames. During rollout, the model maintains a visual key value cache alongside separate keyboard and mouse caches at action-enabled blocks. This ensures every new chunk receives its complete aligned action window, preserving the high-frequency nature of game controls. ForgeWM's training is a progressive 4-stage process that changes the temporal execution pattern, sampling objective, and conditioning history distribution at each step. Stage 0 is bidirectional domain adaptation. We adapt the action condition generator to the target game domain using full-clip bidirectional attention. This learns the visual and control prior without committing to causality. We retain this checkpoint as the frozen real denoiser for later stages. Stage 1 introduces causality via teacher-forced training. We initialize a second branch from the same base and replace full attention with blockwise causal attention. Frames within a latent chunk attend bidirectionally, but each chunk can only attend to earlier chunks. Crucially, training uses clean history. A block mask ensures noisy chunk I attends to clean chunks j less than I and to itself. This teaches the causal execution pattern and action to latent alignment without exposing the model to rollout errors. The objective is a teacher-forced flow matching loss where the history is exact. Stage 2 bridges the gap to few-step generation through causal consistency initialization. We perform online causal consistency distillation. We initialize the generator, an exponential moving average copy, and a frozen teacher from the stage 1 checkpoint. We use a discrete grid of 48 noise levels and sample an adjacent pair per step. The frozen teacher takes a classifier-free guided Euler step from sigma I to sigma I plus 1. The student's clean prediction is then matched to the EMA stop gradient at the teacher advance point. This local consistency objective initializes few-step sampling without an offline trajectory dataset. Ablations confirm this is the stage that enables effective few-step sampling, driving the largest reduction in LPIPS. Stage 3 is on-policy distribution matching. This closes the train test gap. The student performs auto-regressive self-rollout, conditioning on its own generated history. We use distribution matching distillation to align the student with the domain teacher. The gradient direction is formed from the disagreement between a frozen real denoiser and a trainable fake denoiser. Specifically, the gradient G is the difference between the fake and real denoiser predictions, normalized by the mean absolute deviation, acting as an adaptive normalizer. This direction is applied through a generator surrogate loss. Training on the induced rollout distribution reduces the clean history mismatch left by teacher forcing. We train separate budget-specialized students for 1, 2, and 4 steps. Note that 1 step and 2 step refer to the steady-state denoising budget, though the first generated chunk uses a fixed 4-step schedule for enhancement. Deployment uses a dual-path protocol. For online interaction, you use the budget-specialized student for low latency. ForgeWM also introduces Replay-Time Refinement. After interaction, you can take the saved draft, renoise it at an intermediate flow timer R, and denoise it again using the deployed student under the recorded actions. The renoise chunk is computed, as z of r equals 1 minus r times the draft plus r times epsilon. The student denoises this under the aligned action window and the refined causal prefix. This refines local visual detail while preserving the draft's viewpoint and scene layout. Replay matches 4-step reference quality while remaining roughly 3 times closer to the experienced trajectory than regeneration from noise. This requires no second checkpoint or parameter updates. The results demonstrate ForgeWM's effectiveness. On paired Minecraft trajectories, ForgeWM variants attain the best values in 6 of 7 quality and control columns. ForgeWM1 achieves the highest generation throughput. ForgeWM2 and ForgeWM4 rank first on K-control, indicating the highest action sign accuracy under counterfactual opposite action pairs. Human preference studies show ForgeWM4 receives 68.8% of visual quality preferences and 57.6% of action accuracy preferences. This recipe also transfers to different control spaces. ForgeWM Cross FPS applies the same 4-stage progression to first-person shooter gameplay with gamepad controls. The continuous control input width is widened from 2 to 4 channels, grafted from the base checkpoint to preserve symmetry breaking. The result is a 4-step causal student that maintains causal consistency across games like Halo Infinite and Modern Warfare. ForgeWM presents a robust framework for few-step interactive world models. By progressively enforcing causality, consistency, and on-policy distribution matching, it preserves game-native controls even under aggressive sampling compression. The dual-path deployment with Replay-Time Refinement offers a practical mechanism to balance latency and quality. This work provides a clear path toward controllable, low-latency video generation that can respond reliably to complex frame rate control streams. For the full technical details, including the optimization hyperparameters, stage-wise ablations, and the cross-FPS adaptation specifics, check the link in the description. Thanks for watching, and keep exploring the latest in AI research.